No one bird is the same, even birds of the same family. And I believe every single pilot would agree with this. Now think about an aircraft, even of the same family. Hi there, my name is Percy. No one pilot is the same, and no operator is the same either. But there's one common thing between every single operator. It's understanding how to reduce the cost drivers in the private jet operations. In the previous video, we explored the cost-benefit of traceability maintenance history and the close monitoring of corrosion, the highest cost driver in operating an aircraft. In this video, we'll explore corrosion engineering in turbofan maintenance cost, the highest percentage of direct maintenance cost. And again, we're on the same case study, Falcon 7X first C-check mentioned in the first video. A modern turbofan engine often operates 25,000 hours, equivalent to flying to the moon and back 27 times. Besides the engine itself, where corrosion always finds its way through, there are other environmental parts and assemblies that need careful attention. Thrust reverser, where again, on that Falcon 7X first C-check, due to lack of traceability and close monitoring, major repairs could have been avoided or at least largely mitigated. Well, someone paid for it, whether or not in full knowledge of the facts. Let's have a look at a section cut of a turbofan and see in a simplified way how things work inside. In a turbofan, air enters the intake, gets compressed by the compressor. The compressed air moves through the diffuser into the combustor or the combustion chamber, where it gets mixed with fuel, gets ignited, creating heat and expanding gases coming out from the back of the engine. Push the turbine wheel, powering the compressor to complete the cycle, as well as producing thrust. Thrust reverser relationship. The higher the speed of the jet, the greater the thrust force, making the aircraft move forward, all in one continuous cycle in a linear fashion, also called the Brayton cycle. Air is the working fluid. The rotating blades of the compressor add energy to the fluid, and its temperature and pressure rise to a level suitable to sustain combustion. The compressor receives the energy for the rotation from a turbine, which is placed right after the combustion chamber. The synchronized operation of the compression, combustion chamber, and turbine make the aircraft moves forward. A fantastic piece of technology. Engines are designed as a series of modules for ease of assembly and subsequent maintenance. Each module has its individual identity, service history, and designated levels of work. The core modules, the hot section of an engine, consist of a high-pressure compressor, the combustor, the combustion chamber, and a high-pressure turbine, and are generally restored at each shop visit. The life-limited parts are governed by flight cycles, defined by the OEM in the Engine Manual, Chapter 5. Turbofan maintenance is an unconditioned process. The determination of continued airworthiness is largely done through trial monitoring analysis. The typical monitored parameters being the exhaust gas temperature, usually called the EGT margin, the rotor shaft speed, fuel flow and consumption, oil pressure, engine vibration, and chip detector. And as mentioned, the design follows a modular concept. This modular design essentially dictates how engine maintenance is managed. During a shop visit, any of the individual modules can be removed and restored as an individual unit. The breakdown of an engine shop visit process is as such. Engine disassembly. Disassembly into engine modules. Full disassembly of modules into piece parts if necessary. Parts inspection. Cleaning of parts, NDT for detecting cracks. Dimensional checks on blades and vanes. Repair and replacement. Part repair in workshops. Replacement of non-repairable parts. Certification and reassembly. Certification of refurbished parts. Balancing of rotables. Reassembly of module units. And finally, engine testing and release. Testing of the engine on wing and in test cell. Updating of engine documents. The primary cost driver of engine shop maintenance is material cost. Approximately 60 to 70% of the cost of an engine shop visit is due to replacement of material. If life-limited parts require replacement, the material cost will increase further. Direct labor will account for approximately 20 to 30% of total cost, while repairs will account for 10 to 20%. Something to keep in mind. Life-limited part replacement during a light shop visit would increase the necessary work scope and therefore the cost. Hardware deterioration. All engine components are exposed to different kinds of deterioration mechanism. This includes low and high cycle fatigue, thermomechanical fatigue, corrosion, other unscheduled removal causes, FOD, oil leak, high oil consumption, vibration, airworthiness directives, among others. On that Falcon 7X first C-check, the operator asked me, well, how do you reduce costs knowing the operational challenges? There's always lessons to be learned, and the devil is in the detail. Engine maintenance costs are largely influenced by its associated shop visit rate. As for the thrust reverser, the maintenance process is an unconditioned, impacting average time on wing. The interval is mainly influenced by accumulated flight hours and flight cycles. Its cost variable is largely labor-driven and includes costs to overhaul and repair components. Now back to the engine. An example of engine performance degradation is flight operation, and precisely average flight length. As the flight length reduces, an engine spends a large proportion of total flight time using takeoff and climb power settings. In most instances, the effect of shorter stage length operation is more rapid performance deterioration, leading to greater direct maintenance cost per flight hour, while longer flight lengths equate to higher time on wing and lower direct maintenance cost. At the end of the day, commercial considerations are based on where an engine is in its economic life cycle. So, a relationship exists between time on wing and cost per engine flight hour. One of the most common way of dealing with engine maintenance is the flight hour agreement. It does have some advantages that certainly are not negligible, but there's one major disadvantage in the flight hour agreement, and that needs to be considered. Flight hour agreement reduces the aftermarket competition. It creates situations where there is no aftermarket competition on any level and where the OEM controls all commercial aspects. It's common knowledge, and I'm very well placed to affirm this. In a management program that focuses on analytics, data is collected from assets in the field, analyzed, and then used to optimize the delivery of maintenance. Let's dig deeper in corrosion mechanism in gas turbine. There is one form of corrosion that exists in the blistering environment of a turbine engine hot section, and it's called sulfidation. The galvanic corrosion that eats away aircraft structures exists at normal temperature and is an electrochemical process. Sulfidation is a chemical process that exists in high temperature environments. Mechanical erosion, like pitting, FOD, cracking, and burning, is the main form of damage to engine compressor and turbine sections. How does sulfur get into the engine in the first place? Rust never sleeps. All hydrocarbon or petroleum-based fuels contain trace amounts of sulfur. After refining, no engine is immune from this process. And since sulfidation tends to form in the blade root, shroud, and to a lesser extent on the blade airfoil, it is a serious matter that requires constant monitoring. And all this causes the engine to be less efficient, more expensive to operate, and more fuel consumption. Big question, if? Well, what if data had been analyzed from previous maintenance? What if performance was monitored? What if, as mentioned previously, anything that could lead to corrosion was properly checked to avoid unnecessary cost and downtime? What if trend monitoring data were used to better shop visit rate and processes? Why would you handcuff yourself and keep paying money for nothing? Common sense should prevail. Join me next time for some other good news on how to cost control maintenance.